a Portland Community College mathematics telecourse. A course in arithmetic review produced at Portland Community College. This very short lesson simply wishes to reverse the process we had on the last tape. We have a mixed number. Let's go back to its improper form. In this case, let's simply jump right on top of the technique without worrying about the logic behind it. It is simply this. Let's multiply the denominator times the whole number, which is 35. Then let's add that to the top, and 35 plus 2 is 37, and write that over that denominator, which is 7. And we claim that this is the improper fraction form to this mixed number. Now we can prove it even though we didn't go through the logic of getting from here to here. It's fairly simple. But let's work backwards. From the last lesson, this reads 37 divided by 7. 37 divided by 7. And indeed 7 goes into 37 5 times. 5 sevens is 35. Subtract, that leaves a remainder of 2, which we write over the divisor, and see it is exactly where we started. So once again, the denominator times the whole number, that product added to the top gives me my numerator of my improper fraction, and the denominator stayed the same. Let's restate that formally for our notes. And this is a case where in your note a diagram probably can speak much better than a paragraph of words. Starting here, multiply those two, my first step, that's 24. Adding that product to this gives me 29 over the denominator, which stays the same. The denominator times whole number. That product added to the numerator. That becomes the numerator of my improper form. Denominator stays the same. I repeat the technical verbiage primarily so that you can get more and more used to it as we go along. A verbal example. Joseph has 2 3/10 dollars. How many dimes is that? Now, this says he has 2 whole dollars and another dollar which has been divided into 10 equal parts, which we call dimes. He has 3 of those. So now, using our procedures for changing a mixed number to an improper fraction, we multiply the denominator times the whole number, 20, add the sum to the top, 23, and put it over the bottom. So he has 23 of those parts where the whole has been divided into 10 pieces called dimes. Or in short, he has 23 dimes. Another problem. If 1/4 inch represent 5 feet on a scale drawing, how many feet do 2 3/4 inch represent? So each one of these 4th pieces of an inch represents 5 feet. So our question is, how many of these 4th inch pieces does he have? Then I'll multiply it by 5 to find out how many feet that is. So 2 3/4 change to an improper fraction. Multiply these two is 8. Add to that is 11 over 4. So I have 11 1/4-inch pieces. But each one of those is 5 feet. So 5 times those 11 1/4 inches gives me 55 feet. So we could state here that 2 3/4 inch represents the same distance as 55 feet, apparently on a map scale. There it is. Our task is just that simple. To change a mixed number to improper fraction, we simply multiply these two, the denominator times the whole number, that's 42, add to the numerator, 47, put over the original denominator, and you're done. Let's make this a short lesson and leave it right there, easy as it is. So let's jump from that very simple lesson to our continuing reviewing, so that towards the end of this chapter we will be able to use this prime factorization task and other reviews to be able to do a problem like this very, very easily. So to prime factor, we need to first have in memory or before us a list of prime numbers. Here we have such a list. Then we begin a long, it appears in this case, a long series of divisions by prime numbers. And we can cleanly see that 2 will go into this. So dividing it by 2, we get 6,076, and this being even tells me that 2 will still go in at least once more. So dividing this by 2, we get 3,038, which is still divisible by yet another 2. So dividing a third time, we get 1,519, and we have carried the 2's as far as we can. So now we go to the next prime number, and we can see if 3 will divide into it by actually trying to divide by longhand or by calculator, or by using the divisibility test. So 1 and 5 is 6, and 1 is 7, and 9 is 16. 3 will not go into 16, so it will not go into 1,519. So 3 is not a prime divisor. We can see by inspection alone, because this is not 0 or 5, the 5 won't. 7 will just try. So if you try to divide 7 into this number, you'll find that it does go 217 times. Now to see if 7 will go in again, we have to simply try it again. And if we do, it goes in 31 times. But now 31 becomes a prime number, and that's when I quit. So the prime factorization of 12,152 is 1, 2, 3 2's being multiplied together, called 2 cubed, times 7 times 7, which is 7 squared, times 31 to the first, if you wish. So here is the prime factorization of this. Again, review this until you're smooth and very, very comfortable, so that you hardly ever make a mistake or even think seriously about what you're doing. And always keep at the back of your mind, the reason we're doing it is to be able to perform a problem like this within another half dozen lessons or so. So let's just, while we're here, concentrate on this denominator and write it in prime factored form. We've done 32 so many times that perhaps some of you have it memorized already. 2 goes into 32 16 times. 2 goes into that 8. 2 goes into that 4. 2 goes into that 2. This is prime, so 2 times 2 times 2 times 2 times 2, or 2 to the 5th is simply another way of writing 32. So we have prime factored this denominator 2 to the 5th. Now let's extend our review of the last chapter a bit further. Do you recall what is meant by the phrase, the least common multiple of, say, 3, 4, and 6? Do you recall what the phrase was asking us for? Recall that the word multiple, or a multiple, is a number which a given number will divide into evenly. Example. We can say that 15 is a multiple of 3 because 3 divides evenly into 15. But 3 has lots of multiples. 15 is just one of them. And so is 18 a multiple of 3 because 3 divides evenly into 18. Or 48 because 3 divides evenly into 48. So this list of multiples of 3, that is, numbers that 3 will divide into, goes on forever. And of course you can see that 3 is a multiple of itself because 3 certainly goes evenly into 3 once. But say a number like 28 is not a multiple of 3 because 3 will not divide into 28 evenly. Are you beginning to feel comfortable with this word multiple? So going back to our question of just a moment ago, multiples of 3 are all the numbers 3 will go into evenly. And multiples of 4 are all the numbers that 4 will divide into evenly. And multiples of 6 are all the numbers that 6 will go into evenly. Let's look at a list of all the multiples of 3, 4, and 6 each, if that's possible. You see, to list the multiples of 3, 3 is the first one, it's really just a matter, if you will, of counting by 3s. 3, 6, 3 more is 9, 3 more is 12, 3 more is 15, and so on, and so on, and so on. And of course, we eventually realize, hey, this list goes on forever. So there is an infinite number of multiples of 3. Another way we could have looked at this, rather than saying start with the multiple itself, 3, and then add 3 more, add 3 more, add 3 more, add 3 more, we could have begun with our set of natural numbers. There, up here on the bright white spots. We could have said to find the multiples of 3, simply repeatedly take 3 times each of the natural numbers, and so on. 3 times 14 is 42, 3 times 15 is 45, 3 times 16 is 48, and of course this process goes on forever. So if now I wish to find the multiples of 4, I would simply take 4 times 1, 4 times 2, 4 times 3 is 12, 4 times 4 is 16, and so on forever. So now I have a list of the multiples of 4. So you see, multiples is a list, and the list goes on forever. So now if we also want the multiples of 6, 6 times 1, 6 times 2, etc. Is all of this coming back from the last chapter? It's very, very important. So we do have list of the multiples of 3, 4, and 6. But our original question was not what are the multiples of those 3 numbers. We have that. That's 3 lists. But what is the least common multiple? Well, before we answer that, let's back up once more and ask, what do we mean by common multiples? Well, if we begin to look at all three of these lists and look for common numbers, notice this. 12 is a multiple of 3 because 3 goes into it. 12 is a multiple of 4 because 4 goes into it. And 12 is a multiple of 6 because 6 goes evenly into it. Now let's see if there are any more common multiples. See, each of these is a multiple of those three numbers, so it's a common multiple. Whereas 9 is a multiple of that, but not of this or this, so 9 is not a common multiple. So if we search a bit, we will find that 24 is common to each of my list. If we search again, we would find that 36 is common to each of the lists. If we search some more, we find that 48 is also common to each list. So far we have 1, 2, 3, 4 common multiples of the numbers 3, 4, and 6. And the list of common multiples turns out to be a list that is also infinite. It goes on forever. There is no end of numbers, whole numbers, that 3, 4, and 6 will divide into. So now we can move up one word and cleanly see what we mean by least common multiple. Of that infinite list of common multiples, 12 is the least. So 12 is a least common multiple of these three numbers. Another way of stating that would be, what's the one number, the smallest number that exists, that each of these will divide into evenly? And of course, in this case, 12 is it. 3 goes into 12 4 times, 4 goes into 12 3 times, 6 goes into 12 twice. So now, do you have perhaps a clearer and a more comfortable feel for what we mean by the phrase least common multiple, which we will abbreviate as LCM for future lessons? Therefore, after this brief review, you should at least be very comfortable with what is meant by a statement like this. What is a least common multiple of any two numbers, or 3 or 4? What are we really asking for? Well, we're asking for the smallest number in existence that 6 and 10 will each divide into. Now please note that 6 and 10 will both divide into 60, will they not? 6 goes into here 10 times, 10 goes into here 6 times. They will both go into 90. 6 goes into 90 15 times, 10 goes into 90 9 times. They'll both go into 120. There's an infinite number of numbers that these two will go into evenly. But we're asking, what's the least of them? And without too much thinking with two simple numbers like this, and without any work, you'll probably realize it's 30. 30 is the smallest number that each of these will divide into. Most of the numbers you've worked with in the past are such that you can simply inspect the numbers and simply know the least common multiple without doing anything. Just look, know, write it down, or use it. However, here the answer to the question is not so obvious. Not at all obvious, is it? What is the lowest number that each of these will divide into? But at least we can understand what the question is asking. Find a number that both of these will divide into somehow. And is not at all obvious, is it, that this is going to be that number? So within the next 1 or 2 lessons following this, as part of our extended review, assuming then that you at least know what we mean by this phrase least common multiple, and that you also know how to prime factor any number, including rather large ones. We will show you, or remind you, that finding the least common multiple of these two, or any number of numbers, no matter how large, is really quite routine. So while you're doing the next few lessons, you might be reviewing Chapter 2 and asking yourself, how did we do this? Now, can you nail it down so that you're very comfortable in that process? You must be within 3 or 4 more lessons. Now, as important as these reviews will prove to be, let's not in each lesson forget the main topic of that lesson. Therefore, in this lesson, our principal considerations is with problems like this: to change from a mixed number form to improper form. Mixed number means I have a whole number with a fraction. See, we say it in mixed number manner, 3 and 5/7. And we wish to change this to what we've unfortunately learned to call improper fractions. What we really mean is a single pure fraction, which simply means I want to know what the new top will be, what the new bottom will be. 2 questions. Therefore, from a few moments ago, can you see the single point being made in this lesson? It was simple enough. Simply this: to form our new top, or numerator, we first multiplied these two, the denominator times a whole number, that's 21, then added that to the numerator, so that gives me 26, which becomes the numerator of my improper fraction. And then the denominator of my so-called improper fraction simply stays the same as the original fraction. And we remind ourselves that 26/7 is just another way of saying the number 3 and 5/7. In short, these are equivalent, which means they look different, but they have the same value. So once again, bottom times whole number added to top becomes new top, and bottom stays the same. Just that simple. And to encourage you to begin to think more and more verbally, each lesson always gives you some verbal or story problems to try to encourage you to translate from these words to an arithmetic statement. So let's see how we would handle this one. Pies at a corner coffee shop are cut into 6 pieces for each serving. See, we're talking about fractions now. We're dividing a whole, pie in this case, into 6 pieces each pie. How many orders can be filled if they have 12 and 5/6 pies? Well, this tells me how many pieces are in each pie. This tells me one pie has only 5 of those original 6 left. Then, in addition to that, and I have 12 full pies. Well, you can see that if I convert this to a mixed number, leaving the denominator the same, then bottom times whole number is 72, plus 5 is 77. So we have 77 of those 6th-sized piece of pies. So we have 77 servings of those 1/6 of a pie left. Later you'll find that it helps to think of it in this way. I have 77 of, or times, 1/6 of a pie available. Is this beginning to make sense? I trust so. And frequently, towards the end of a lesson, you'll see what appears to be the same problem, but the parts, the numeral parts, are becoming messier or more involved. That's to cause us to realize that just because the numbers get larger, the math procedure does not change. It simply becomes a little bit messier. To change this to improper fraction, the bottom still remains the same. That's simple enough. And to find the new top, we take the bottom times the whole number, and then that added to this top to get to the new top. So see, you can know what to do. In fact, you must know what to do before you even do it. So this simply says the arithmetic is going to be somewhat messy. I'm going to have to multiply 2 and then add that product to that. Well, we simply will multiply by longhand if that's the way we must do it, and be very, very careful and to double check our work, or use a calculator if it's permitted and you have one. So all the calculator does is help us to do whole number arithmetic fast. See, it's not really doing the fraction for us, is it? So we take the bottom times the whole number, which gives me, the bottom times the top number, which gives us a very large number. Well, so be it. Then we must add that product to the top, so plus 13 equals, and we have the top of our improper fraction. The important point we're trying to make is because the numbers get messy, the math doesn't change. Our arithmetic simply becomes somewhat involved or messy, and we simply have to do the same thing more slowly, more carefully, or if you're in the circumstances where it's permitted, use a calculator to do the arithmetic itself of whole numbers. But the fractions, you have to have that procedure in your mind. Most of the problems you'll encounter, however, are so simple you can do the work mentally. Again, when you're changing a mixed number to pure improper fraction, if you will, the denominator stays the same. Then denominator times the whole number is 70, added to the top is 75, and you're done. It's just that simple. So, until your next lesson, this is your host, Bob Fennell.